All right, so yesterday we did our lab on the law of conservation of mechanical energy. Okay. Today we're going to finish up conservation of mechanical energy. Going to go over power, which doesn't take very long. Okay, and then that's it. Tomorrow is your unit exam. Coming right up. Right? Yes. Tomorrow. 17. Yes. I was looking at this one. Okay. Okay, that's you guys. All right. So when we have any instance where mechanical energy is being converted from potential to kinetic, okay, there's at least the potential for all of it to be conserved. Okay. We've talked about roller coasters, sleds going down hills, things like that we treat like they're perfect world situations, but we know better. Okay. But another situation is simple pendulum. Okay, pendulum is just a weight on the end of either a rod or a rope, okay, that swings back and forth and hypnotizes people. Okay, but not really, because I don't know how to do that. Okay, but it swings back and forth. As it's doing this, all it's doing is converting gravitational potential energy into kinetic energy. Okay, back and forth over the same path. All right. Now, obviously, it's not as perfect as this because I'm helping it. Okay, every single time it comes through, I give it just a little bit of a pull to keep it going. Okay, whereas if I didn't do that, it stops fairly quickly. Okay, it loses energy, right? It doesn't work against friction. There's friction here at the pivot point. There's air resistance, all that stuff that steals the energy away. Okay, but what we have to understand is that with a simple pendulum, we start out at the highest point in the arc, okay, where we would only have potential energy, okay, and then we descend from there, okay, and so what's constantly happening is the same as what's happening with a sled or a roller coaster. Potential is converting into kinetic until we get to our lowest point where we would have only kinetic energy, I mean, assuming it can't fall any further here, okay, it's on a rope so it's not going to fall any further than that, okay, and then as it goes back up the other side, it's going to convert that kinetic energy back into potential, and if it was a perfect physical world, it would swing forever. All right, everybody okay with that? Okay, so would we treat that mathematically like we would for anything else? Like for the roller coaster and all of that, EI would still equal EF? Yes, absolutely. Okay, it's just another example of a situation where law of conservation of energy applies. Okay, so if we're looking at this situation here, okay, we've got a 2-meter long strings pulled sideways and released. The highest point of the swing, the pendulum bob, is 25 centimeters or 0.25 meters above the floor. At the lowest point, the pendulum is 5 centimeters above the floor, okay, and the mass of the pendulum bob is 250 grams. So they're asking, what's the mechanical energy of the pendulum relative to the floor when the bob is at its highest point? By the way, the weight on the end of a pendulum is called the bob. Okay, in case you're wondering who Bob was, okay, it's not a person, that's the bob, okay, because it bobs back and forth, I guess, I don't know, that's what they call it. Okay, so if I want to calculate the mechanical energy right here, we just said that's where there's no kinetic. There's no kinetic there because at that point the pendulum bob is not moving, right? That's where it instantaneously changes direction from moving upward to moving downward. Okay, so we have only potential energy there. So our initial mechanical energy is just m times g times h initial. So that would be 250 grams, so 0.250 kilograms, times 9.81 times 0.25 meters, because they told us it was 25 centimeters above the floor. All right, so we're trying to play some unit tricks on us there, but we're too smart for that. Okay, 0.25 times 9.81 times 0.25. All right, so that's the mechanical energy at that point. It is also the mechanical energy on the other side. Where else? Bottom. Where else? Anywhere. Right. Anywhere along this arc, that is the mechanical energy of the pendulum bob. Okay? If the law of conservation of energy holds true, that will never change. How much of it is potential, how much of it is kinetic can change. But that's the number. It's going to be that number no matter where it is along the arc. Okay? Everybody all right with that idea? Okay, so a question like this, if I put this on a test, you'd be surprised how many people do 3 times the math they need to do. All right, so the first part here, what's the mechanical energy of the pendulum? Well, we just figured that out. It was one simple calculation. What's the mechanical energy of the pendulum relative to the floor when the bob is at its lowest point? People will go and they'll do this. Okay, I need to know the potential energy and the kinetic energy, so I got to get all these numbers. I don't know how fast it's going. How am I going to get that? When all they need to realize is it's that number. Okay, it's not changing. That's exactly what this question is testing. Okay, how many marks would part B be out of on a test? One. Okay, remember, look for things like that. If the question is out of 1 mark, how much work do you need to do? 0 work. You need to write down an answer. It's already, you've either already done it or it's right in front of you. Okay? All right, what's the kinetic energy of the bob when it's at its lowest point? This one would, according to how they've written it, would require a little bit of calculating because it does still have some potential energy as it's still 5 centimeters above the floor. Okay, so you'd have to go that 0.613 minus the kinetic energy, okay, would equal, or sorry, minus the potential energy at the bottom would equal the kinetic energy. Okay, that would give us EK. So there would be a tiny bit of math there. Okay, what's the speed of the pendulum bob when the bob is at its lowest point? Okay, well, once I calculate this, okay, it's just a matter of manipulating for VF, just like we would have in a roller coaster question last week. Okay, so just keep in mind that there are a number of different types of situations in which the law of conservation of energy could apply. The most common ones, sleds, roller coasters, pendulums, okay, people jumping out of planes, okay, things like that. Especially if they mention that there's no air resistance or no friction and stuff like that. Okay. All right. I want you guys to try question number 3. I'm just going to make it bigger. Okay, that's the answer right there. Check your work. Right? But I want you guys to try this one. So we got a roller coaster trolley. They tell us the mass. Okay. When it's at the top of the first hill, it's moving at 0.2 meters per second. Hill's 85 meters high. Trolley goes down the first hill and up the crest of a second hill, which is 64 meters above the ground. Ignore the effective frictional forces. What is the kinetic energy of the trolley at the top of the second hill? They're not even asking you to calculate the speed, okay, which would be a little bit more involved. They're only asking for the kinetic energy. Okay, give you a few minutes and see if you get that one. Okay, so on this one here, we're looking at this situation. We got the roller coaster at the top of the first hill, or the highest hill, where its initial speed is 0.2 meters per second and its height is 85 meters. And then a little while later, it's over here on top of this hill. We're looking for its kinetic energy. Okay, and we know that it's 64 meters above the ground. Okay, so what we have is that EI equals EF. That is, the mechanical energy here and the mechanical energy here are the same. Right? At that first point, do we have potential energy? Do we have kinetic energy? We have both, right? It's moving and it's above the ground. Right? So in that first case, I've got initial potential plus initial kinetic, and at the end here, I also have both. Okay, I'm lower, so I'm obviously going faster, okay, and have kinetic energy, and still 64 meters above the ground. Okay, they only want me to calculate EK final. So how do I get that by itself right now? Subtract EP final over to the other side. Okay, so that's going to then look like this. Initial potential plus initial kinetic, or initial mechanical energy, minus the final potential energy will give me the final kinetic energy. Okay, that's all I'm looking for. I don't have to go any further than that to find the speed or anything. So I'm just going to plug in my formulas. M times G times H initial plus 1/2 mv initial squared minus mgh final equals ek final. Now, in other questions, we canceled the mass. Can I do that here? I can't. Okay? The reason I can't is I'm looking for the energy, not the speed or the height. Okay? When I'm looking for speed or height, those are not dependent on the mass. They're just the result of gravitational acceleration. But here I'm looking for energy, and energy is dependent on mass. If the trolley were heavier, it would have more energy. Do you want to follow me on that? Okay, plus the units for joules for energy are kilogram meters squared per second squared. I have to have the mass in there. Okay. So if I'm plugging in my numbers, okay, they said it was 840 kilograms. So 840 times 9.81 times 85. So there's my initial potential, plus 1/2 times 840 times 0.2 squared, so it's not very much kinetic energy, it's not moving very fast, minus 840 times 9.81 times 64 meters. That'll give me my final kinetic energy, which should come out to 1.73 times 10 to the 5 joules. Okay. Could that question have also asked you to calculate the final speed? Would you have been able to calculate mass, or sorry, cancel mass then? Yes. Okay. Do you have to? No. All right. Is everyone okay with that one? I'm going to do one more. I'm going to do the pole vaulter question. So I'm going to have you guys try the pole vaulter question here, number 4. Okay, and we're going to walk through that. Then we're going to do power. Then we'll probably come back and do a few more conservation of energy questions before class is over. All right, so give number 4 a try here. Okay, the first part is a calculation thing, but B is talking about you have to describe the changes in energy that occur, okay, as a result of pole vault. I don't know, have you guys watched pole vault before? You know what pole vault looks like? Okay, you know what, maybe. Okay, so here's what we know. Initially, because we're dealing with the vaulter's center of mass, okay, so it's like here, just kind of below your chest, okay, is where your center of mass is located usually, okay, that is 0.850 meters above the ground. So we have to go with that as our initial height, okay, and we know that they are approaching with a speed of 8 meters per second, so that's our initial speed, right? How fast are they going when they go over the bar? 0. Yeah, okay, there is that moment where they're at the peak of their height where they're technically not moving. Okay? I mean, in the real world, they would probably have a little bit of horizontal motion, but we're going to simplify things and say that they're not moving. Okay, so their final speed is 0 meters per second. We're looking for the final height of the pole vaulter. Okay, which sets us up for this. The mechanical energy of the pole vaulter, the idea in pole vault is to convert all of the energy you have built on the ground into height. Okay, so the faster you can run and the more efficiently you can bend the pole, okay, the higher you will go. That's what it's all based around. So EI equals EF. We want to convert our initial mechanical energy, which is a very small amount of potential, plus a fairly large amount of kinetic, into our final mechanical energy, which is going to be all potential. Everyone with me so far? All right. So now, okay, I can plug in my formulas. M times G times H initial plus 1/2 MV initial squared equals MGH final. What can I cancel? Mass, yeah, I don't need it. I can leave it in if I want to, but in this case, I'm not looking for energy, I'm looking for height, so I don't need the mass, okay? So I'm going to get rid of that, so I got one less thing to punch in my calculator, and I'm going to divide both sides by G in order to get my final height. So I'll have 9.81 times 0.85 meters plus 1/2 times 8 squared divided by 9.81. And that should give me 4.11 meters as my final height, which is an impressive pole vault. Okay? I used to coach track and field. I can count on one hand the number of times I actually saw somebody go over 4 meters. Okay? Most of the time, pole vault is high jump with a stick at the high school level. Okay? They just kind of run and pivot over the pole. Okay? Now, when we're talking about someone who's doing pole vault the right way, okay, there are a number of energy conversions that come into play. Okay? Obviously, at the beginning, we're just trying to build up speed. Okay? And it didn't. The video we watched didn't do it justice. But these pole vaulters run fast. Okay? Like you're running full bore, holding onto a stick that you're going to plunge into the ground and then hold on for dear life. Okay? Now, once they've got all of that kinetic energy, okay, and they plant the pole, what does the kinetic energy do to the pole? It bends it. Okay, what kind of energy are we putting in the pole if we change its shape and it wants to snap back? Elastic. Okay, so we're converting kinetic energy into elastic potential energy in the pole. Okay, and the more of it you can get into the pole, the better. Okay, and you have to be careful. Pole vault poles have a bendy side and a stiff side. That's how they store their potential energy. If they were bendy on both sides, you'd just bend them. It'd be like a pool noodle, okay? And it wouldn't be very effective. So one side is stiff, the other side is bendy. If you get that thing rotated in your hand and plant it upside down, it will snap. When you are fully committed and upside down, that is the moment it will snap. Okay? I've seen that happen a number of times and watched people come down on their heads. Okay, so you have to be very careful when you're converting your kinetic energy into elastic potential energy. Now, once that pole is bent, its maximum amount, it starts to convert your elastic potential energy back into kinetic. It accelerates you, but it accelerates you upwards. Okay, so it's turning that elastic potential energy into kinetic and some potential, and then once you let go of the pole, okay, you still have some kinetic energy that's going to turn into potential energy as you go over the top. Okay, you'll notice that each one of those athletes, as they went over, okay, pushed the pole away. Okay, not that they had to; it could have easily just fallen through because it was shorter than where the bar was. Okay, but if you're going over the bar and your pole is higher than the bar, you have to push it away. If it knocks the bar off, it's a fall. Okay, so they're converting. Okay, that elastic potential, then a little bit of kinetic into potential energy, and then that potential energy converts back into kinetic as they fall to the mat. Okay, everyone kind of follow me on that? All right, let's talk about power. So this should be the last thing in your notes package for this unit. Now, the good news about power is that there will be no problem solving to do with it. Okay, so there'll be no mathematically based questions on the unit exam about power. Okay, all we need to know is basically what power is and what can affect it. Okay, and that's all. So very simply, power is the rate at which work gets done. Right? The more powerful something is, the faster it will do work. Right? Easiest comparisons for that would be if you had a 800 watt hair dryer and a 1500 watt hair dryer. Okay, which one will dry your hair faster? The 1500 watt. Okay, watts are the units for power. A watt is a joule per second. So a 1500 watt hair dryer puts out 1500 joules of energy every second. Okay, drying your hair far faster than an 800 watt hair dryer would do the same job. Okay, similarly, if I have a 2 horsepower electric lawnmower and a 5 horsepower gas lawnmower, which one will mow my lawn faster? The gas one. Okay? Can they both mow my lawn? Absolutely. But one will take longer. I can't walk as fast behind the 2 horsepower one because it won't keep up. Okay? It'll bog down, okay, and it won't cut the grass properly. I have to walk slower because it can't spin the blade either as fast or as forcefully as the 5 horsepower gas mower, so it will take me longer to mow my lawn with the less powerful lawnmower. Is that making sense? Okay, so that's really the gist of power. Okay? All right, so these two 1997 Honda Civics, okay? This one's stock, just the way you would have bought it off the showroom floor in 1997 before you were born, okay? It was not a very powerful machine, 0 to 60 in 2 weeks, okay? You were downhill with the wind, and somebody was rowing out the window, okay? So, was not a very powerful machine, but if you gave it to Vin Diesel, okay, who could like pimp it out in Fast and Furious, well, then he'd throw a couple of turbos and an intercooler and a whole bunch of other crap on there, okay, to make it much, much more powerful. Okay, can they both get to 60 miles an hour? Absolutely, but this one will do that work faster. So it's the same amount of work. Okay, they're both on Civics. They both can get to 60 miles an hour, but one can do it faster because it's more powerful. Okay, everyone okay with that? Okay, so the idea of power incorporates the concepts of both work and time. So here's the thing we have to understand, because oftentimes people think the wrong way about power, okay? And they say that this hydroelectric dam can do more work than this one. Okay, it's not true. If I run this one for 2 seconds, and this one for 150 years, they will do the same amount of work. Okay? This one is more powerful, so it will work faster. That's the key to power, and that's the mistake most people make. They say it's more powerful, it can do more work. Practically, yes, because time is always a factor. Okay? But from a strictly physical point of view, no. Anything can do the same amount of work. It just will take longer. Okay? That's what power is, the rate at which you do work. Okay? All right, so the units for work are watts. Okay? And a watt is a joule per second because it's work divided by time. And the units for work are joules, and the units for time are seconds, which is a watt. Okay? So if you're at home and you have an old-fashioned 60-watt incandescent light bulb, that's the kind with the tungsten filament inside, okay, it will use 60 joules of energy every second that it's on. You can replace it with a 4-watt LED bulb. Now, how is it that a 4-watt LED bulb can do the same job as a 60-watt incandescent bulb? It's not supposed to generate light quicker. In this case, the watts are the amount of energy being used, not the amount of light being generated. Okay? This is where efficiency comes in. A 60-watt light bulb is more powerful than a 4-watt LED bulb. But in this case, that power is bad. Okay? Okay? That power is bad because the incandescent light bulb is doing more work or using more energy every second because it's not just generating light. It's also generating heat. Okay? So in this case, it's more efficient to go with the less powerful object because it's not about all of that energy, it's about just the part of it that we want, the light, not the heat. Okay? All right with that. So sometimes having the thing that's got more watts is not necessarily good. Okay? In some cases it is, but in the case of something consuming energy, we also have to find kind of that tipping point. Okay? If I compare, let's say, like a really massive muscle car, it's got 710 horsepower or whatever, okay, and then I put it next to a Tesla, which is all electric, okay, is it better to have all the horsepower, or is it better to have the Tesla? The Tesla will likely win because it's more efficient, okay? It doesn't have to be more powerful. It's going to make better use of the joules that it's being given, okay, and not waste them and turn them into sound and heat and tire smoke and all the really cool stuff that happens, okay? But, okay, like a Tesla just takes off and goes. It doesn't look terribly impressive, but it's fast, okay? The other one just spins its wheels and looks cool. All right, everyone okay with the idea of what a watt is? Joule per second? Okay. Right, now, oftentimes people ask this, well, units for power are watts, then why do we use horsepower, okay, for certain things? And the answer is, well, the metric system wasn't around, first off, okay, when all these ideas first came about. And we use horsepower for cars and any kind of internal combustion engines because the initial purpose of the internal combustion engine was to replace horses. Okay? It made perfect sense to have units that were labeled as horsepower. That way, Farmer John can come in and go, I got these like 4 old nags that I need to take to the glue factory, okay, and I need to replace them. Do you have something with the power of 4 horses that will do their job? Okay, and that's what, so tractors were initially put in horsepower because that's what they were replacing, and that just stuck. Okay, like now, if you go to a car dealership when you're shopping for a new car, they will actually have the power rating, especially on hybrid and electric vehicles, not in horsepower. It'll be in watts, which is a meaningless number to most of us. Okay, if I walk up to a sticker and it says to me that this car is 2.5 kilowatts, I look at that and go, is that good? Is that fast? Because I don't know. Okay, can you tell me how many horsepower it is? Because that's a meaningful number for me. Okay, if it's 300 or more, okay, all right. If it's like less than 100, no, I don't want that. It's not going to be any fun. All right. So that's where this unit came from. So to give you an idea, 1 horse will do 746 watts worth of power. Okay, that is 746 joules per second. Okay, is what a horse can generate. So if you put them on a treadmill, and connected it to a bunch of light bulbs, they can light up just about 800 watt light bulbs. They ran really, really fast. Okay, that's the power of a horse. 746 watts. All right, that one we don't have to do because we're not doing the math. Okay, we're going to look at something strange. It's an exercise to help us review some work energy theorem as well as some power applications. There was this paper that came out a while ago. It was a comic book. It was a comic, actually, that explored the geopolitical consequences of having Superman turn a crank to provide unlimited energy to the world. And whether there would be any, social consequences, or, maybe that wouldn't be fair to Superman. Would that be enslavement? But I mean, Superman has an unlimited source of energy apparently, and he kept turning this crank. He could power the whole world. Superman's fake, but the idea was there. These are the kinds of things people talk about. Okay, so this guy that Mr. Dickey and I found online was doing a similar thing with Yoda. Because, well, Yoda's infinitely cooler than Superman. Okay, so how much power could Yoda generate? Okay, so I take him down to Pincher Creek, okay, where all the wind turbines are. Okay, and Yoda goes down there and he sees all the wind turbines and he goes, rotate your wheel, power make you. Okay. Not bad? What's that? Okay, awesome. When my kids were little, they always wanted me to read them Star Wars stories, and I had to do all the voices. Plus, I'm a total nerd, and yeah, nerds do. Okay, so how much power could Yoda generate if he was turning all the turbines with the Force? Okay, that kind of thing. So, what this guy did is he looked at some of the things that Yoda did in, of course, just the original 3 movies, because after that, everything kind of becomes a travesty. We won't get into that, okay? But it does. Okay? So we're going to look at a clip from the greatest movie of all time, The Empire Strikes Back. Okay? It is the greatest movie of all time. Okay? We're going to look at a scene from that, okay, where Yoda is training Luke Skywalker. Okay? And he's teaching him the importance of essentially like believing in himself. trusting or giving himself to the force, okay, and trusting in the force, which is kind of an allusion to what we do as Catholics, which is you're supposed to surrender yourself and have faith that God will take care of things. That's kind of an allusion to that. Okay, you surrender yourself to the force, and the will of the force will guide you, okay, or enable you to do things. So what we're going to look at here is how powerful was Yoda when he was lifting Luke's X-wing out of the swamp, okay, and putting it back down on the ground. All right. So we're going to watch that clip first because it's awesome. Okay. And then we're going to go back and we're going to do this stuff here. In the original trilogy was when he lifted Luke's X-wing from the swamp. As far as physically moving objects around, and of course, if you were watching this in the order it was meant to be watched, which is 4, 5, 6, then all the others, okay? This would have been the most impressive thing you would have seen up until then, okay? You guys have seen all the other stuff where Jedi are like Superman, okay? So this was the easiest thing, or this was the hugest thing that we ever saw, okay? So the energy it takes to lift an object to a certain height is equal to the object's mass times gravity times height, okay? So first we need to know how heavy the ship was, okay? The X-wing's mass has never been canonically established. That means it's not in canon. The thing that like really nerdy people know, okay? But its length has, for some reason. It's 12.5 meters long, okay? An actual fighter jet, the F-22, is 19 meters long and weighs 19,700 kilograms. So we're going to scale that back and say that the X-wing has a mass of about 5,600 kilograms. Okay, so now we have a mass to work with. Okay, next we need to know how fast it was rising. Okay, so he went over the footage of the scene and timed the X-wing's rate of ascent as it was emerging from the water. You thought I was nerdy. Okay, this guy watched that scene with a stopwatch. Okay, and he timed it. All right. So the front landing strut rises out of the water in about 3.5 seconds. He estimated the strut to be 1.4 meters long, based on a scene from Star Wars: A New Hope, Episode 4, okay, where a person had to duck to get underneath the X-wing, so about 1.4 meters. Okay, so that tells us, okay, that it went 1.4 meters in the 3.5 seconds. So we could calculate the speed at which it was rising. Okay. Lastly, we need to know the strength of gravity on Dagobah, because this is not on Earth. Yoda lived on Dagobah. Okay? Now, here he figures he's pretty stuck because while sci-fi fans are obsessive, it's not like there's going to be a catalog of minor geophysical characteristics for every planet visited in the Star Wars universe. Wrong. How dare he doubt the nerddom? Okay? Because there's apparently this thing called Wikipedia. Chewbacca is a Wookiee, so it's like Wikipedia exactly for Star Wars. Okay? And it does have just such a catalog of the accelerations due to gravity on every planet in the Star Wars universe. Why? I don't know. But we have these kinds of things because they're necessary. Okay? So, gravity on Dagobah is 0.9 G. That is 90% of Earth. That means that on Dagobah, the acceleration due to gravity is 8.829. That'd be pretty handy if you were playing sports. You'd be able to jump a lot higher and lift more weight, okay, because acceleration due to gravity would be less. All right, so now we know, okay, 8.829 is G. All right, so we want to calculate the rate at which, okay, the work is being done. Right, so we know that he's lifting at 1.4 meters, okay, and we know that power is work divided by time. So the work he does is the change in potential energy divided by the time, which they told us was 3.5 seconds. Okay, so if we take our 5,600 kilograms times 8.829 times 1.4 meters, we'll get the amount of work required to lift an X-wing out of a swamp, because that's stuff we need to know. Okay, Now we got to divide that by 3.5 seconds, because that's how long it took to do it. All right, so 19,776 watts, so about 20 kilowatts. Okay, 20,000 watts. Okay, that's about 25 horsepower. I mean, Yoda's small. 25 horsepower is not bad. He's doing the work of 25 horses. Okay, it's about the amount of power in the motor of an electric model smart car. So it's not all that powerful. Now it's like it really kind of puts a damper on the whole thing. Okay, so at current electricity prices, Yoda would be worth about $2 an hour. That's nowhere close to minimum wage. It ain't easy being green. Okay, so if we look at other examples in Star Wars of power, okay, like force power, there's also like the shooting the lightning out of their fingers. Okay, to do that would require not kilowatts, but megawatts, maybe even gigawatts, okay, of power to make electricity arc through the air. Okay, so obviously there's far more power out there to be had than just lifting stuff. Okay, Yoda hardly lifted a finger, okay, to move that ship compared to what he's probably capable of doing. Right? All right, so if we're looking at, okay, a free body diagram of this, okay, so just as a quick review on how to draw a free body diagram, what are some of the forces that would have been acting on the ship? Force of gravity, okay? What else? Okay, air resistance for part of it, water resistance probably for another because it was underwater, probably it had like swamp weeds all over it. They were probably holding it down too. There would have been probably a few other resisting forces. So we'll just put force resisting. That could include friction and everything else that was, you know, even suction of the landing gear in the mud. Yeah. Force Yoda. Okay, going upwards. Right? Those would have been. So this isn't as simple as what we did. We said he was only overcoming this force. This force could have been just as big. Okay, all the other stuff that was holding the X-Wing down inside the swamp. So Yoda might have been even more powerful than that, okay, than what we calculated. All right, so that answers kind of number 2. Okay, he probably had to do more work than that. Now, assuming there was no air resistance, once he had lifted the X-Wing out of the swamp, he moved it horizontally through the air. Did he do any work during that part? Okay, remember, the definition of work is that there's a change in mechanical energy. He moved it at a constant speed through the air. No, didn't require any work at all. It was already above the ground. He had already done the work. Okay, moving something without changing its height or speed means there's no change in energy, thus there's no work being done. So that would have been the easy part. Okay, you just move it through the air like that. All right, that makes sense to everybody. Just to have a little fun. Yeah. Okay, before we get into these, I'm going to give you guys a quick break, but all right, so for this one, okay, this is what we got. Start of a 12-meter high hill, okay, and it starts from rest. What's the speed of the roller coaster when it's 4 meters above the ground? So that would be down here. Okay, that's the stuff we, sorry, we're looking for the speed. Okay, we're looking for the speed here, okay, if it's 4 meters above the ground. All right, so do I have potential energy at the beginning? Do I have kinetic energy at the beginning? No, okay, not moving. All right, so we got our initial mechanical equals our final mechanical. Our initial mechanical is all potential. Our final mechanical is some potential and some kinetic. Okay, what I'm looking for is part of the kinetic energy, so I need to bring the final potential over to this side, like so. Whoop. Okay, so m times g times h initial, okay, minus m times g times h final equals 1/2 mv final squared. What can I cancel? Mass. Is that a good thing in this question? Yeah, because they didn't give it to me. Not that it matters, right? But they didn't give it to me. So I'm going to cancel that off, divide both sides by 1/2, and then square root, and that'll give me my VF. Okay, so VF will be the square root of 9.81 times 12 minus 9.81 times 4, or just 9.81 times 8 would also work. Okay, divided by 1/2, all square rooted should give us 13 meters per second. Okay. Everybody all right with that? All right. Now, something to be aware of on your unit exam tomorrow. Okay, you're going to have a law of conservation of energy question, but remember there could be a part B, okay, that has to do with work energy theorem, right, and stopping the object once it reaches the bottom. Something that was giving people trouble on question number 2 on the review. Okay, people were interpreting question number 2 in the review that the sled was still on the hill, but it said it was at the bottom. Sorry, it's question number 1. Okay, it was already at the bottom, and people weren't realizing that, and they were doing the question like it was an inclined plane when it was simply a friction problem. All right, this is our last one. It's both work energy theorem and conservation of energy. Okay, so it's giving you a force and a distance. Okay, and it's asking you what's the speed at the target 5 meters away. Now that's going to assume that it travels horizontally, okay, from this point to this point. Give you a couple minutes on that one, then we'll go through it, and that'll be it for this unit. Okay, so let's have a look at this one. Where does the arrow get its energy from? Well, it is kinetic, but where does it get its kinetic energy from? Right, from the person pulling back the bow. Okay, when I pull back a bow, I exert a force through a distance. I'm doing work. Okay, so can I calculate the work? Yeah, I know it's 12 newtons. I know it's over 0.3 meters. Okay, so 12 times 0.3. Okay. Right, so we're looking at 3.6 joules. All right, so that's how much work the person does in drawing back the bow. That's how much energy the bow arrow system will ever have. Okay, since it doesn't mention anything about the arrow losing any energy over the 5 meters it travels to the target, this is how much energy it has when it hits the target. Okay, assuming that's all kinetic, can I calculate how fast it's going? Yes, absolutely. Okay, I would just say EK equals 1/2 mv squared. Okay, divide both sides by 1/2 of m and square root. Okay, and I've got V. Now this arrow is ridiculously heavy. Okay, it has the same mass as almost 1/2 liter of water. Okay, no arrow has that mass. It should have been 0.045 kilograms. Okay, or it was like 40 grams instead of 450 grams. It's really heavy. Okay. All right, so when we do that, okay, we should get it that it's moving at 4 meters per second when it hits the target, which is really slow for an arrow. You could totally be a ninja and reach out and catch it and snatch it out of the air. Don't try that. Mythbusters did it. They had a mechanical hand that reached out and grabbed it. They had a guy who tried it and couldn't do it. Don't try to catch an arrow. Don't try to outrun a bullet. Neither one of those works. Okay? Yeah? So physics advice. Helpful physics advice. Save your life one day. Okay? All right. Tomorrow is your unit exam. You can start at noon. All right? If you want to start early, I will be here at noon. Come in, drop off your phone, and I'll give you your test, and you can start at noon, and that'll give you an extra 20 minutes to write the test. Okay?